Hi, my name is Akshay and this is Half Sleeves. Before starting the video, I would tell you that in most of the video we will be building some mathematical foundation for the understanding of GANs, and in the later part of the video we will make the connection between the GANs and the mathematical theory. Also, further in the video we are going to minimize and maximize a two variable function. Usually the maximization and the minimization is done theoretically through equations. So before doing that, I want to give you a graphical idea of how that works. So this curved surface you see is called a paraboloid, and the minimum point of this curve is here, which means here at this point the curve has the lowest possible value. The equation of this curve is x minus 2 whole square minus y minus 2 whole square, and the minus 2 in the xy coordinates just means that the center of the paraboloid is at 2, 2. To find this minimum point mathematically, we would have to minimize the paraboloid function fxy over x and y, which can also be written as this: minimizing the function over x, and then when it's minimized over x, minimizing it over y. It means we are minimizing it in parts rather than simultaneously minimizing it. This minimization is like asking the question, what should be the value of my x and y so that I get minimum possible value of fxy. Now let's say we wanted to find the minimum point of this paraboloid. How would you do that? How would that process of minimizing this paraboloid would look like graphically if we found the minimum in parts? That is, by first minimizing the function over x and then minimizing it over y. Let's first minimize the function over x. For that, we will first choose a y. Let's say y is equal to 2. Choosing a y is just like taking a plane and cutting the paraboloid curve with that plane at y equals to 2. The place where the plane intersects with the curve is represented by this black parabola curve. Here you should notice that y is fixed at 2, but x is completely free to move anywhere on the x-axis from left to right. But what we want to do is minimize the function at x. So at what value of x this function is minimum? It is very obvious to see that the function is minimum at this point. You should notice that once we choose the minimum point on x-axis, the x coordinate, which was earlier free to move on the x-axis, is now fixed at the minimum point and it cannot move. By the way, just as a side note, you can on your own try plugging y equals to 2 in the paraboloid equation which was shown earlier, and you will get an equation of a parabola. Similarly, we can take y equals to 4, take a plane and cut the paraboloid curve with that plane at y equals to 4, which will give up a parabola curve like here. And now we can minimize the curve over x by asking at what value of x this function is minimum. It is very obvious to see that at this point the function is minimum. Again, we can repeat this process for y equals to 4 or 6 and minimize the parabola curve. We have only chosen 3 y values here, but we can select any y value we want. We can choose y equals to 1.2 or y equals to 1.5. In fact, we can choose any real number out of the infinite many real numbers on that y-axis and repeat this process. Choosing one value from y-axis gives us one black parabola. So let's say we do this process on all the infinite many real numbers of y-axis. That would give us infinite many such black parabolas. What that means is that y can take any value it wants from the infinite many real numbers on the y-axis, but x cannot do so. X cannot take any value it wants from the infinite many real numbers on the x-axis. In fact, it has a constraint. that it can take only one and only one value, and that value is that blue dot where the function is minimum. So in the equation of the paraboloid, we will fix the x coordinate because we have minimized it, and it is fixed or it is bound to that minimum point. This is the original equation. This is the equation with x fixed. If x is fixed, it means that it is constant, and that means that the function now is of only one variable, which is y. In fact, we can treat the x coordinate as a constant c, and if we do that, the new equation we get is of a parabola. So if we join all these blue dots with a white curve, we get a white parabola facing the y-axis, which means that now y is free to move anywhere it wants, but x is fixed at one place. Well, this process of choosing different y's and finding the minimum over x, which we just did, that's what minimization of this function over x looks like. So originally we wanted to do two things: minimize the function over x and then minimize it over y. And it is shown by this equation. Till now we have minimized our function over x and our first goal is complete. But we found after that minimization over x that the function only depends on y and is a function of y and only y. So we can plug this value in the above equation and we are left with minimizing y over a function of y, which is quite easy. Minimizing y over a function of y just means like asking a question, what is the minimum point of this white parabola? Which is very simple to see that this point is the minimum. This point is not only the minimum of y but minimum of both x and y, because all the points on this white curve were already the minimum of x. So we have achieved our final goal, which is represented by this function. Now that we have seen the visualizations of minimization, let's move towards how the Gan works. Let's say we have two people or two players, one Boltzmann and the other Bohm. Boltzmann will be represented by the symbol capital B with a subscript Z, and I'll call it BZ. And Bohm will be represented by the capital B with a subscript M, and I'll call it BM. Let's say Bohm and Boltzmann are playing a game. The rules of the game are as follows. Boltzmann and Bohm both will select a number, a real number, any real number. The real number Boltzmann selects will be called X with a subscript Z, and I'll call it XZ. And the number chosen by Bohm would be called Y but with a subscript M, and I'll call it YM. Now that both of them have selected a real number, we will choose a two-variable function. We have chosen this function, but any two-variable function can be chosen. Now the numbers xz and ym are given as inputs to the chosen two-variable function fxy. So this function will output a z value, which will be the value of the function on xz and ym. And the game is that whatever is the value of z, Bohm will pay z amount to Boltzmann. So yes, that is the game. The two players choose two numbers, we find the value of a two variable function on these two chosen points, and then Bohm will pay Boltzmann amount equal to the value of that two variable function on those two chosen points. This type of a game is called a zero-sum game, which means that the sum of the amount lost by Bohm and the amount gained by Boltzmann would be zero. Which means if Bohm pays Boltzmann Z amount, the amount lost by Bohm will be minus Z, obviously, and the amount gained by Boltzmann would be plus Z. So the sum of plus Z and minus Z is zero, and it is a zero-sum game. A zero-sum game is the mathematical way of saying that there are no external influences on our game. Let's say that the amount lost by Bohm was minus Z. and the amount gained by Boltzmann was z plus 5. That means Boltzmann gained extra 5 amount from someplace else other than Bohm. So there is an external factor affecting this game. External factor other than two players who are playing the game, Boltzmann and Bohm. So the zero-sum condition is for ensuring that there are no external factors affecting our game. Boltzmann is receiving money from Bohm. So Boltzmann would like to maximize the amount Z he's getting from Bohm because he wants to get more money. Who doesn't want to get more money? The only way he can maximize the amount Z he's getting from Bohm is by changing X because he only has control over X. So the only thing he can do is change X, but he has to change or choose the value of X in such a way that it maximizes the function fxy or maximizes the amount Z which he gets from Bohm. So Boltzmann would try to maximize the function fxy over X, and xz is the value which maximizes the function over X. So Boltzmann has chosen the value xz, which means that the x variable of this function is fixed and y is free, which means that this function fxzy is a function of only one variable, that is y. Now after Boltzmann, Bohm will also choose a real number ym, but how will he choose it? Bohm is losing money in this game, so Bohm would want to minimize the amount he is losing to Boltzmann because he doesn't want to lose money. The only way he can minimize the amount Z he's losing to Boltzmann is by changing Y because he only has control over Y. So the only thing he can do is change Y. But he has to change or choose the value of Y in such a way that minimizes the function fxzy or minimizes the amount he's losing. So Bohm would try to minimize the function fxzy over y, and as we saw earlier that the function fxzy is a function of only one variable, which is y. So ym is the value which minimizes the function fxzy over y. What this means is that in this game, one of the player is trying to maximize the function and the other is trying to minimize it. So in this game, we are just maximizing the function and then minimizing it. Now, when I saw this for the first time, I was confused that how can we maximize and minimize a function at the same time? Because I could visualize a maximum point of a function or a minimum point, but how do I visualize such minimizing and maximizing points at the same time? Well, this equation for maximizing and minimizing a function looks a lot like the equation for minimizing the two variable paraboloid function which we saw earlier. So we can use the same method which we used to find the minimum point to visualize this minimum maximum point. By the way, just to remind, the equation of our current Boltzmann-Bohm game function looks like this. And here is how this equation surface graph looks like. Let's first try to maximize this function over x. Just like the paraboloid, we will choose a y and cut the graph on that y value. We can see that the plane cuts or intersects the curve in an inverted parabola, which is facing the x-axis. Now, here you should notice that y is fixed at 6, but x is completely free to move anywhere on the x-axis from left to right. But since our aim is to maximize over x, we can ask the question, for what value of x is this function maximum? It is very obvious to see that at this point the function is maximum. Again, we can repeat this process of choosing a y, cutting the curve at that point, drawing a parabola curve where the plane and the saddle curve meets, and maximizing the function over x for different values of y. In fact, we can repeat this process for all the infinite values of y, and if we do that, we get infinite such black inverted parabola curves. If we look at all these curves separately, we can observe that x is now always fixed blue dot and cannot move. It is fixed at the maximum point, but y can move freely and can attain any value it wants. Y can be any real value from the infinite many real numbers on y-axis. So this process of choosing different y's and finding maximum over x we did That's what exactly maximization of this function over x looks like. If we join all these blue dots with this orange line, we get a parabola facing the y-axis. This parabola is what is left of our original function after maximization over x. So now the maximization over x is complete. As you can see, x is fixed for this orange curve and y is free, and that is why the function after maximization is a function of only y and not x, because x is fixed and y is free. Now we have finished the first part and maximizing the function over x. In the next step, we want to minimize the already maximized function over y. So we take this orange parabola and ask the question, at what value of y this curve would be minimum? And the simple answer would be here at this point. So the minimum maximum point we were looking for on this curve was this point, which is at the intersection of this orange curve and this black curve with the dotted lines. This minimum maximum point exists here at this white curve. By the way, this white curve is called a saddle curve. So minimum maximum point would be here. This point is called minimax in short, or the saddle point. Now we are ready to answer the question, where does all this fits with GANs? Well, GANs are also basically two players playing a minimax zero-sum game with each other. One player is the critic and the other is generator. Let's say Bohm is the critic and Boltzmann is the generator. And the function which would decide how much amount each player gets is still dependent only on the output of our players. That is, output of the critic and the generator. The difference is that in GANs, this function is called a loss function or a cost function. And this is denoted by this capital L with a subscript C. This function can be anything. Generator's aim is to output such a number xz which maximizes the loss function and increases the critic's loss, which is another way of saying that generator should choose its weights such that it outputs a picture which increases the value of loss function or maximizes it or makes it difficult for the critic to differentiate it from the real image, while the critic's aim is to output such a number ym that minimizes the loss function, which already has the value of generator's output. That means that once the generator has already outputted a picture and given it to the critic to differentiate, the critic should be able to output a number 0 or 1 and differentiate between real and generated picture. Z denoted the output of the two-variable function for Boltzmann and Bohm's case. In case of Boltzmann and Bohm, Z denotes the amount each player gained. Here, for critic and generator, the output of the two-variable function is denoted by LC, or the output of the loss function. The output of the two-variable loss function, or LC, can be thought of as how much money each player lost, which means that more the loss is, more money is lost. So, LC is equivalent to minus Z, because they both are opposite of each other. So, if the generator is doing good, then it would increase the critic's loss, which means that the critic would lose Z amount of money, and thus its gain would be minus Z. And since it is a zero-sum game, the gain of generator for performing good and increasing the critic's loss would be plus Z. The interesting part is that our two-variable loss function can also be negative, and that would mean that the critic is doing good as it is losing minus Z amount of money. Well, losing minus Z amount is just like gaining plus Z amount. And since it is a zero-sum game, the gain of the generator would be minus Z. We have already seen how the minimization and maximization happens graphically. Next, let's see how it happens in GANs numerically. Next, I will explain in brief the process of gradient descent and ascent through numerical or formula approach. If you already know this and you know how it works in GANs, you can skip this section. So, this is our function fxy, which outputs a value z, where x and y are generator and critic's output. Remember, generator wants to maximize and critic wants to minimize this function, or I should say this loss function. This is the gradient of this two variable function, and this is a vector, and its components or elements are the partial derivatives of the two variable function fxy with respect to x and with respect to y. This partial derivative with respect to x is just the slope of the two variable function in the x direction, which means that in which direction you should move on x axis to increase the value of function fxy as quickly as possible. The same goes for the partial derivative with respect to y. The gradient descent actually shows the direction of steepest ascent. This means that which direction is the quickest way up. Let's say you are at a point x0 y0 on this graph. The first question which you should be asking to maximize this function is that whether you should add something to your current position x0 y0 or subtract something from your current position x0 y0 to increase the value of the function fxy. Well, the components of the gradients answer exactly that question, and they tell you whether you should add something to your current position or to subtract something from your current position x0 y0 to increase the value of the function fxy as quickly as possible. This is like asking which direction you should move to increase the function. So if the components of the gradients are positive, that would mean that you would add those components to the current position x0 y0 to maximize the function fxy. And if the components are negative, you would still add those components to the current position x0 y0 to maximize the function fxy, because adding a negative value is equivalent to subtracting. And this addition to the current point x0 y0 will give you your new coordinates x0 plus 1 and y0 plus 1. This eta constant which we multiply to gradients before adding is called learning rate. It is always some small value, usually lesser than 1. Why are we multiplying with a learning rate? Let's just look at y component. Let's say if we have a two variable function and this is how it changes with y. And let's say you are at the point y0. Let's say you calculated the gradient for this two variable function, and let's say that the y component of the gradient is positive, which means that it is telling you to increase the function over y, you should move in this direction or increase the value of y. Remember, it has just told you which direction you should move in, but not by how much to move. It has told you to add something to your current position, but not how much to add. So let's say you add the value of y component of the gradient to y0 without the learning rate. Now it is possible that the value of the gradient is too big. What do I mean by that? Let's say you add the gradient to your current position y0 and move to the point y0 plus gradient of y, which means on graph of the function you would have moved to this point, but you wanted to go to this point, the maximum of the function, and now you have added too much to the current position y0 and have left behind the maximum point and reached to the other side of the graph. So as a solution to this over addition, we can add small amount of gradient to the current position y0. To do that, we will multiply the gradient with a small constant like 0.01 and then add to the current position y0. If we do that, we will reach this point, and then we can repeat the same process to move small distances closer to the maximum point and eventually reach it. There's one more question which I will leave up to you. How we will know when to stop or when have we reached the maximum? A hint would be that the slope or the gradient values get smaller and smaller as we move closer to the maximum or minimum. Just one last thing, you remember that the critic is trying to minimize the function and the gradient shows the direction of the steepest ascent or the direction of the maximum. So to get the direction of the minimum, we just have to reverse the sign of the gradient's y variable or y component, as y is the critic's output and it wants to go in the opposite direction to what gradients is showing. So our new y coordinate y0 plus 1 would be given by subtracting the gradient from the current y value y0. In the next video, we will understand what is the fundamental problem with GANs, or I should say, the problems with this minimization and maximization framework of GANs.